Welcome to AP Calculus 1.7a. Thank you to Mark Sparks for providing the curriculum that we're using for this lesson today. This lesson, 1.7, we're actually looking at two very closely related concepts. The first is infinite limits, or limits that when I find the limit of a function, I get infinity or negative infinity as a result. We can see an example of these in this function on the left graphically. If I were to take the limit as x approaches 2 or 1 from the left or from the right, so I approach 2 from the left, approaching from the left, I approach negative infinity. This is an infinite limit because it is a limit that results in a positive or negative infinity as x approaches some number a, where a is a real number. So infinite limits are limits that result in infinity as our x value approaches some number. And these will always result in a vertical asymptote. This is important because we may be asked to find a limit as x approaches a that gives me a positive infinity or negative infinity, and then may be asked to give the graphical significance of that limit, in which case its significance is that there's a vertical asymptote there. More often, you're likely to be asked to find the vertical asymptotes of the function and justify their existence. We can find each of these limits from the graph. As x approaches 2 from the left, we said approaches negative infinity. As x approaches 2 from the right, we're heading off toward positive infinity. How about the limit as x approaches negative 1 from the left and from the right? As I approach negative 1, I approach, looks like negative 1/2 or 1/3 from the left. And as I approach negative 1 this way, I approach negative 1/2. So as x approaches negative 1, I approach negative 1/2. These would not be infinite limits because I'm not finding a value approaching infinity as I take those limits. We'll come back to this function on the right in a couple pages. We've seen how to find these infinite limits in a previous lesson, lesson 1.2. And as you'll recall, our infinite limits are vertical asymptotes, our limits that yield infinity. We found these by finding a factor in the denominator that would not cancel out. And then we could determine, does it approach positive infinity or does it approach negative infinity? By taking a value very close to a, this is our a, by evaluating for a value very close to a, that would give me an indication as to whether it was trending toward positive infinity or trending toward negative infinity. Let's look at these. We'll do one together and then you can try the other three on your own first. I would start by factoring to find out what factors will not cancel. If I were to simply plug 2 directly in, I would get undefined 0 into the denominator. So we'll factor these and get 2x plus 3 times x plus 2 over x plus 2 times x minus 2. And this is the limit as x approaches 2 from the left. And I can cancel my x plus 2's, leaving the limit of 2x plus 3 over x minus 2 as x approaches 2 from the left. And if I were to plug this 2 in, I would find my denominator is still 0, my function is still undefined, which means that to actually find this one-sided limit, my two-sided limit does not exist, because I can't further cancel this and evaluate it. But my one-sided limit can exist. It's just going to not be a real number. One-sided limits do not have to be a real number. So as I approach from the left, that is from a slightly lesser value of 2, I will evaluate this for 1.9. 1x equals 1.9. This gives me 2 times 1.9 plus 2 over 1.9 minus 2. And this in the numerator, I don't have to work it out exactly. I can tell that this would be positive. Positive times positive plus positive would be positive. And 1.9 minus 2 would be a negative. Therefore, this limit approaches negative infinity. Positive divided by a negative yields negative infinity. At this time, go ahead and try. We'll call these limits 2, 3, and 4. Cancel. And then the key here is that to justify our existence, we must go through this process of canceling and then taking a value very close from the correct side in order to find what my limit is. That finds my limit, and that also justifies the existence of our vertical asymptote, which we'll look at in more detail at the bottom of the page here. Go ahead and come back. I'll show you the answers. You can check your work and then rework anything that you may need to. Okay, here we are. Answer to number 2 is infinity. Answer number 3 was infinity. And answer to number 4 is negative infinity. Let's look at working each of these problems. Number 2, this is the same factorization. So this is equal to the limit as x approaches 2 from the right of 2x plus 3 times x plus 2 over x plus 2 over x minus 2. And same thing, our x plus 2's cancel, leaving us the limit. Remember, when we're taking the limit, we can cancel things, and we still have the same limit. It's only a function that we can't cancel and still have the same value. So our limit as x approaches 2 from the right of 2x plus 3 over x minus 2. And I want to find this limit. I see that x minus 2 won't cancel, and it still gives me 0 in the denominator. So I need to take my limit by finding, is this positive infinity or negative infinity, by choosing a value very close to 2 but slightly greater than. That would be 2.1. So if x equals 2.1, then 2x plus 3 over x minus 2 equals 2.1 times 2, got that a little backwards there, but it'll work, plus 3 over 2.1 minus 2. This numerator will be positive. The denominator, 2.1 minus 2, will also be positive. Therefore, this equals positive infinity. Same page, but number 3. We have a new function here, x squared minus x plus 1 over 2x plus 2. And I go ahead and check. If I evaluate at negative 1, I get negative 2 plus 2 is 0. So this function is undefined. I want to see if I can find the limit now by factoring and canceling. So I take the limit as x approaches negative 1 from the right, and I factor numerator x minus 1. Oh, wait, no. X squared minus x plus 1 does not factor. If this were 2x, that would factor. But this is a form you should become familiar with if you haven't already, that simply doesn't factor, which means I'm just finding the limit, x squared minus x plus 1. I can factor the denominator, though, and that's 2 times x plus 1. That doesn't really do me any good because I can't cancel anything, even though this is a limit and technically I would be allowed to. There's nothing here for me to actually cancel. So we will try taking a value very close to negative 1, but just greater than, which would be negative 0.9. If x is negative 0.9, and y is this function here, x squared minus x plus 1, 2 times x plus 1. this is my value. Then I can plug in that negative 0.9, negative 0.9 squared minus negative 0.9 plus 1 over 2 times negative 0.9 plus 1. We just want to look at this closely. Negative squared is going to be positive. Minus a negative is going to be positive, so plus a positive, and then plus 1 is going to leave a positive in the numerator. In the denominator, negative 0.9 plus 1 is 0.1, or a positive. So positive times a positive is positive, and that yields positive infinity. Number 4 is the same function. I still cannot factor the numerator, and so I can't cancel anything. I can factor the denominator just to make it a little bit easier to evaluate. This one asks, as x approaches 1 from the left, from negative 1, as x approaches negative 1 from the left, from just the lesser than, that's going to be negative 1.1. So we can set up our graph. X is negative 1.1, our table here. And y is x squared minus x plus 1 over 2 times x plus 1. And then I evaluate this at negative 1.1. Negative 1.1 squared minus negative 1.1 plus 1 over 2 times negative 1.1 plus 1. In the numerator again, my negative squared is positive, minus a negative is positive, plus 1. It's going to give me a positive in the numerator. My denominator, negative 1.1 plus 1 is negative 0.1. Positive times negative is a negative. Positive divided by a negative is going to give me negative infinity. Scrolling down then, we find that this infinite limit, whenever the value of my limit is infinity or negative infinity, I have a vertical asymptote. A vertical asymptote. Through precalculus, we can find these graphical attributes, the vertical asymptote, by finding a function in which a factor in the function would not cancel out of the denominator. It would not cancel out of the denominator. However, this is not a viable justification for the existence of a vertical asymptote in calculus. It's not enough. On the AP Calculus exam, they will ask you to find where a vertical asymptote exists and to justify its existence. And you need to do that using limits. You have two options for justifying the existence of a vertical asymptote using limits. X equals A, some value A, is a vertical asymptote. We could also say a vertical asymptote exists at x equals A. It is a vertical asymptote of the function if and only if. This is your only means of justifying. If and only if. You have two choices here. The limit as x approaches A from the left equals either positive or negative infinity, or the limit as x approaches A from the right of the function equals plus or minus infinity. So in other words, if we need to justify the existence of that vertical asymptote, I need to take a limit as x approaches that value A where I've determined through observation that the asymptote exists. I can find out where it is through observation, but to justify that, I need to find the limit as x approaches A from the left, or the limit as x approaches a from the right. So either one-sided limit, I'll get either a positive or a negative infinity out, and that will justify the existence of my vertical asymptote. We can see that with this function down here. If I factor this, h of x equals 2x plus 1, x plus 3, x minus 1, and x plus 3. And this isn't a limit. They didn't ask me to find the limit as x approaches anything from the left. They didn't ask me to find the limit as x approaches anything from the right. They asked me to find any vertical asymptotes and then justify that using a limit. And let's color code that a little bit. Finding my asymptote I can do through observation. Which factor in the denominator does not cancel out? Our vertical asymptote is our factor, where our factor in the denominator does not cancel. This is in contrast to our factor that does cancel. Our factor that does cancel, that's our point discontinuity. So here we would say, from these we could find that we have a point discontinuity at x equals -3, because that's what would make this factor 0. But that can cancel out. My function can still approach that value from both sides, whatever it would be. That leaves me this x minus 1. This gives me my asymptote. This is my infinite limit. Okay. This factor, x minus 1, and that's going to be x minus 1 equals 0 at x equals 1. So when x equals 1 is an asymptote of h of x, and that's vertical. We'll talk about horizontal in the next half of the lesson. Is a vertical asymptote of h of x. That's great, but that is not sufficient because they also asked me to justify my answer using limits, and this does not justify using limits. I don't even have a limit here. To justify this answer using a limit, to justify it, I need to first set up what will that limit be. If I haven't written a limit, I haven't justified it using a limit. So I'm going to take the limit as x approaches, and I've determined my asymptote, my vertical asymptote. My infinite limit is going to be at x minus 1, or I could say that that's if it's where x minus 1 equals 0, we have that right here, then my vertical asymptote's at x equals 1. So I'm going to take the limit as x approaches 1, and we could choose from the left or from the right. I'm going to go from the left. You could do from the right. The limit of h of x equals, and the whole point here for it to be a vertical asymptote is that this is going to equal either positive or negative infinity. I'm just going to write infinity now, and we'll go back and add a positive or a negative once we find that limit. To find the limit as x approaches 1 from the left, we'll set up our numerical table, and my x just less than 1 is 0.9. And my y, I'm going to go ahead and use the simplified form. Because I'm finding a limit, I can use my canceled form. And 0.9 times 2 will be positive, plus 1 is positive. 0.9 minus 1 will be negative. And so this limit, positive over negative, will be a negative, and this will approach negative infinity. I have then justified my answer using a limit because I've shown this limit approaches negative infinity using the numerical approach.